Encoder. Encoder is a logic circuit. Logic circuit is also called as digital circuit. An encoder is a logic circuit that produces a binary value output based upon the active input. Okay, here an encoder has a binary output. So binary output value. See here, an encoder has binary value output. So output of the encoder is binary. And here for 2 power n inputs, there will be n outputs. 2 power n inputs, n outputs. A standard encoder circuit allows one input to be active at a time. Only one input will be active. That means only one input will have logic 1. Remaining will be 0. So a standard encoder circuit allows one input to be active at a time. So at a time you can give only one input. Active means input will be 1, remaining inputs will be 0. An example of an encoder is the octal to binary encoder, whose truth table is given below. So here this is the truth table of octal to binary encoder. Octal to binary encoder. Input is octal, output is binary. So let us see the inputs and outputs. So here you have D0 to D7, D0 to D7. So here the subscript 0, 1, 2, 3 up to so on 7 represents the octal input. And we are going to get the binary equivalent of the octal as the output. So let us see the truth table. So D0 is equal to 1, remaining inputs 0. So here you can see only one input is active. Active means logic 1. So at a time you will be having only one active input. So here D0 equal, here if you see the first row, D0 equal to 1 and remaining inputs equal to 0. So here you are going to get the output as 0, 0, 0. So 0, 0, 0 is the decimal here. 0, 0, 0 is the binary equivalent of the octal 0. Next, see the second row. So see the second row. See the second row. So here D1 is equal to 1. Remaining all are 0. Now here you are going to get the output as 0, 0, 1, which is the binary equivalent of the input octal 1. So let us see the third row. See the third row. D2 is equal to 1. Remaining inputs is equal to 0. So here you are going to get the output as 0, 1, 0, which is the here. See. D2 equal to 1, remaining inputs equal to 0. We are going to get 0, 1, 0, which is the binary equivalent of the octal input 2. Next, see the next row. So here D3 equal to 1, remaining inputs equal to 0. So 3 is the octal input, right? Now here we are going to get 0, 1, 1 as the output. So this is the binary equivalent of the input octal 3. Similarly, you can see 4, 5, 6, 7. So if you take 7, D7, if D7 equal to 1 and remaining inputs equal to 0, you are going to get, see here, 1, 1, 1, which is the binary equivalent of the input octal 7. So here the subscript, here you can see subscripts 0, 1, 2, 3 up to so on 7. This represents octal input. and we are going to get the output as binary equivalent of the input octal. So here you can see here the encoder will have binary value as output. So encoder, name itself, encoding. Encoder means output will be binary. So this is about the encoder. Now let us see the encoder circuit. So octal to binary encoder circuit. So here, before going to the circuit, we have to get the expression for the outputs x, y, and z. Now here, the output x equal to 1 for D4, D5, D6, D7. So here x can be written as D4 plus D5 plus D6 plus D7. Similarly, y. So y equal to 1 for D2, D3, next D6 and D7. So y can be written as D2 plus D3 plus D6 plus D7. Now coming to the Z, the expression for Z can be written as, so first see the truth table, Z equal to 1 for D1, D3, D5, D7. So Z can be written as Z equal to D1 plus D3, D1 plus D3 plus D5 plus D7. So we got the expressions for X, Y, and Z. Next, once you get the expression for X, Y, Z, you can draw the circuit diagram. So here, this is the circuit diagram. See here, X equal to D4 plus D5 plus D6 plus D7. So D4, D5, D6, D7 are given to a OR gate, and the output is X. Next, Y, D2 plus D3 plus D6 plus D7. D2 plus D3 plus D6 plus D7. See here, this dot represents the interconnection. Dot represents the interconnection, right? So here you can see the dot. Dot represents the interconnection. Dot represents connection, right? Next, Z. Z equal to D1 plus D3 plus D5 plus D7. So D1 plus D3 plus D5 plus D7 gives Z. So this is the circuit diagram of octal to binary encoder. So here in encoder, only one input will be active at a time. Now here the same circuit you can simulate using a multisim. So here this is the circuit of multisim. Are you able to see the screen? Yeah, please respond.
Yes, sir.
Okay. Now here you can see here VCC means logic 1, which is 10 volts. Okay. And here you can see the ground. You can see the ground here, right? Here we have VCC, here we have the ground, and here there is SPDT switch. See here, SPDT switch. SPDT switch means single pole double throw. SPDT switch is single pole double throw. So these are the SPDT switches. Now here, when the switch is connected to VCC, D0 here, suppose if D0 is connected to VCC, then D0 will be having a logic 1. Now here D0 is connected to ground, right? D0 is connected to ground. So it will be having a value of logic 0. If the switch is connected to VCC, it will have the value logic 1. If the switch is connected to ground, it will have logic 0. So here the switch can take the position here or this position. These two are the switch positions. The switch can be connected to VCC or the switch can be connected to ground. So here this is the switch. It can move up and down. So when the switch is connected to VCC, D0 will be having a value logic 1. When the switch is connected to ground, D0 will have the value logic 0. Now here, so here D0 is not connected to any of the gate, right? See here, D0 is not connected to any of the OR gates, right? Next here, if you see D1, so if you see this first OR gate, this is a 4-input OR gate whose IC number is 4072. So to the X, what are the inputs? What are the inputs connected? D4, D5, D6, D7. So D4, D5, D6, D7 are connected to this first OR gate, and the output of this OR gate is X. So here there is a probe. So when the, it will on when the input is logic 1. So when the output of this OR gate is logic 1, this light will get turned on. So this you are going to do in a simulation. This diagram I am showing only for the sake of knowledge. Here this diagram you are going to use in the DELD lab. Similarly here the second OR gate, the inputs are D2, D3, D6, D7. So D2, D3, D6, D7 are connected to this second OR gate. Similarly, D1, D3, D5, D7 are connected to this third OR gate. So here this is the circuit in multi-sim. So here one important point is the standard encoder circuit allows one input to be active at a time. At a time, you can have only one input at a time. One input to be active at a time. Active means logic 1. So here if you see this, only one input is active at a time. So if you see the first row, only D0 is active. Second row, D1 is active. Third row, D2 is active. Remaining all are zeros. If you see any row, only one input will be having active input. Remaining will be zeros. Suppose if you give two inputs as active values, that is two inputs to be logic 1, you are going to get a invalid output, or the output will be wrong. So you are going to get the correct output only if one input is active. That is, if only one input is equal to logic 1, then you are going to get the binary equivalent of the input octal. You cannot give two inputs at a time. So this is the standard encoder. So here the input is octal, output is binary. So always encoder will have binary output. If you have any doubts in this encoder, you can ask me. If you don't have any doubts, I will go for the priority encoder. Okay, next one is the priority encoder. So in this priority encoder, a priority encoder is an encoder circuit that includes the priority function. So what is meant by this priority function? So I will explain. The operation of the priority encoder is such that if two or more inputs are equal to 1 at the same time, the input having the highest priority will take precedence. See here, in this, more than one input can be active at a time. So here, if you see this truth table, so if you see the first row, all are zeros. So output is invalid, and V0 is equal to V equal to 0. V equal to 0 states the output is invalid. Next, see the second row. See this second row. D0 equal to 1. So we are going to get the 0, 0 as the binary output. So here this is a 4:2 encoder. So 4 inputs, 2 outputs. These are the 2 outputs, right? xy is the output, and v states the valid or invalid. V states valid input or invalid input. So if v equal to 1, so valid output means v will be 1. Invalid means v equal to 0. These points are explained here. So here I am going to explain about 4:2 priority encoder. See here, D0 equal to 1. So output will be 0, 0. 0, 0. 0, 0 is the binary equivalent of the input 0. Next, see this row. Here this cross represents 1 or 0. It can be 1 or it can be 0. Either 1 or 0. If it is 1, you can see both the inputs are 1 at a time. So here priority will be given for D1. So here these points are discussed here. See here, the excess X or don't care conditions that designate the fact that the binary value may be either equal to 0 or 1. Let us take this one. Input D3 has the highest priority. Suppose all are equal to 1. See here, X can be treated as 0 or 1. If all are 1, then what must be the output? Output is equal to 1, 1, which is the binary equivalent of 3. So D3 will be given the highest priority. D3 will be given the highest priority. Next D2, next D1, next D0. So here the input D3 has the highest priority. So regardless of the values of the other inputs, when this input is 1, the output XY is 1, 1. See here, in this priority encoder, you can have more than 1 active inputs, but the output will be, so we are going to get the output for the highest priority input. So if all the inputs are equal to 1, D0 equal to 1, D1 equal to 1, D2 equal to 1, D3 equal to 1. So here the highest priority is given for D3, next D2, next D1, next D0. So as D3 equal to 1, we are going to get 1, 1, which is the binary equivalent of the number 3, right? So here the input D3 has the highest priority. So regardless of the values of the other inputs, when this input is 1, the output for XY is 1, 1. So XY is the output. XY is the output, and the output is 1, 1, which is the binary equivalent of number 3. So binary equivalent of 3. Next, D2 has the next priority level. The output is 1, 0 if D2 is equal to 1, provided that D3 equal to 0. If D3 equal to 0 and D2 equal to 1, then you are going to get the output as 1, 0. In this case, you can here, regardless of the values of other two lower priority inputs. What are the lower priority inputs here? D1 and D0. So whatever may be the values of D1 and D0, if D2 equal to 1, you are going to get the output as 1, 0. Similarly, the output for D1 is generated only if higher priority inputs are 0 and so on down the priority level. So the order of priority is, so first priority is given for D3, next D2, next D1, next D1, next D0. So this is the order of priority. So D3 will be having the highest priority. Next level D2 will have the priority. Next D1, next D0. So here this priority encoder is there for your DELD lab. So here V stands for valid, right? So a valid output indicator designated by V is set to 1 only when one or more of the inputs are equal to 1. If all inputs are 0, V equal to 0, and other two outputs of the circuit are not used. If V equal to 1, then only the outputs are used. If V equal to 0, the outputs are not used. So here now we have to design the circuit. So here for designing the circuit, we have to get the expression for X and Y using the K-map. So we see here. So what is the first combination? All zeros. So you have don't care for X and don't care for Y. So when all the inputs are equal to 0, so you have this don't care. Next, what is the next combination? 0 0 0 1.
Sir,
Yes,
audible, sir.
Yeah, tell me.
Sir, XY, sir, XY.
Just a minute, I will keep the earphones. Yes, you can tell me now.
Sir, XY అర్థం సార్ XY అర్థం కాదు సార్ XY
ఇక్కడ
XY వాల్యూ 0 1 సార్ XY వాల్యూ XY వాల్యూ 0 1 ఇక్కడ సార్ అదే స్టార్టింగ్
ఇదా
ఇన్పుట్
ఫస్ట్ రోనా
ఫస్ట్ అన్ని లైన్ చెప్పండి సార్ అంటే x కి y 0 ఎప్పుడు వచ్చింది 1 ఎప్పుడు వచ్చింది సార్
సో హియర్ వాట్ ఇస్ ద ఎయిమ్ ఆఫ్ దిస్ సర్క్యూట్ నో సో హియర్ వాట్ ఇస్ ద here what is the output we are getting? We are getting the binary equivalent of the decimal input, right? If no input is there, how can you get the output? Output you cannot take 0, output you cannot take 1, right? If no input is there, how you can get the values at the output? See here, D0 equal to 1, okay? So we are going to get the binary equivalent of 0. What is the binary equivalent of 0? 0 0. Okay.
yes sir
If you see this encoder, see the encoder, all are not equal to 0. At least one will have the active input. At least one row will have logic 1, that is active input. In this, that case is not given here. In priority encoder, we have considered all zeros also. Okay. So here in this case, you can have more than one logic 1 input. So X denotes 1 or 0, whatever may be the value of D0. If D1 equal to 1, we are going to get the output as 0 1. We are going to get the binary equivalent of this 1, right? Suppose if D2 equal to 1, we are going to get 1 0. If D3 equal to 1, regardless of the values of the other inputs, that is lower priority level. If D3 equal to 1, we are going to get 1 1 as the output. So this will be used in analog to digital converters. So here, if you see the combinations, you can take the combinations. So what is the first combination? All zeros. So first combination is all zeros. The output is don't care. You cannot put 1 or you cannot put 0. 0 percent D0 will be the active input. But in this case, you cannot put 0. You cannot put 1. So here you can see D2 equal to 1 means you are going to get X as 1. D3 equal to 1 means you can see the value of X equal to 1. Suppose if all are zeros, the value of X is don't care. So like this here, you can see the second combination 1 0 0 0 X equal to 0. 1 0 0, 0. Here 0. For the sake of convenience, I have not taken zeros. Anyway, we are going to combine the squares having 1. So I have not taken 0. Empty means 0 here. Next, see here, very important one. If you see this one, so what are the possible combinations? So first, 0, 0, 1, 0, 0. Next, 1, 1, 0, 0. See here, if you put x, if you treat x as 0, you are going to take 0, 1, 0, 0. If you take x equal to 1, 1, 1, 0, 0. For these both cases, the value of x equal to 0. So 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, right? So like this. So for this, how many combinations you are going to get? Take x equal to 1 or take x equal to 0, 0, 0, 0, 1, 0. Next, like this, you can take, you are going to get 4 combinations for this one. So here for this, you have 2 combinations. For this row, you are going to have 4 combinations. What are the combinations? 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0. For these 4 cases, the value of x equal to 1. So you can write all the values like this. So here, after this, you can combine these squares. You can combine these squares. You are going to get the expression for x as d2 plus d3. Similarly, for y also, you are going to get the values. After writing the values, you are going to get y as d3 plus d1, d2 dash. So here, this is the circuit. The inputs are d0, d1, d2, d3.